Now, in many of the problems that we will be doing when we are studying turning effects of moments, they have to do with locating all the forces, because once you know the location of a force, then you can also find its distance from the pivot. And since the moment is force into distance, you need to know where the force is, how far is it away from the pivot, in order to find its distance from the pivot. Now, for that to happen, you need to be able to first identify where the center of gravity of an object is. For that, just take a look at this meter rule, the first one, which is on top. If I were to give you a prism and I say let's balance this prism, let's place this meter rule on the prism in such a way that it becomes balanced, where would you place it? Well, probably you would place it at the 50 centimeter mark, and we all know intuitively to do that, but what is the reason behind it? That's where we need to understand what's going on. Well, mass of anything or the weight of anything is not uh, just located at one point, although we do draw the weight as one single arrow originating from a single point, but it's not really just all concentrated at one point. So we know that this meter rule is basically uh, uniform, so it has mass uniformly distributed because it's made up of very small atoms, and all of those atoms have their own weight, so the weight will be distributed throughout this meter rule. But obviously we don't draw the weight of any object as a force like this, so to really make this easy for us, we have come up with a concept of center of gravity. And this is any point on an object where you can assume that the force of weight, the force of gravity, is basically just acting from that point. Now, for this meter rule, the center of gravity must be at its center. If it's a uniform meter rule, if it's made out of material of same density throughout its body, then this is where you can draw the weight of the object from. Uh, what is going to happen in this scenario, in the second meter rule? You probably know that this one is going to rotate like this. It will rotate in anti-clockwise direction, and it will fall down. So why would that happen? Well, because now you already know that the center of gravity of this meter rule is somewhere at the 50 centimeter mark, and this is where the weight is going to be. And you can see from the diagram very clearly that this force is to the left of the pivot, so it produces an anti-clockwise moment. And similarly, if you look at this diagram, the prism is now at the 20 centimeter mark, and we have an intuition of a situation like this, that this meter rule is going to rotate clockwise and it's going to fall to the right. And again, the reason is center of gravity is at the 50 centimeter mark, so the weight produces a clockwise moment because it is to the right of the pivot. Now, you might be asked to identify the center of gravity of different objects, and you would be probably given a situation like this. So let's say I have the screwdriver, and we all know that the screwdriver is not completely made out of the same material. The actual screwdriver, the one thing that opens the screw, is made out of a metal, and the place that you hold it from is made out of rubber or a plastic. So let's say I give you a screwdriver and I say, well, it's balanced on a prism which is placed here, and then you are asked to identify the position of center of gravity. Now, from the meter rule example above, you have to think that if this screwdriver is balanced right now, then and there are no other forces acting on the screwdriver, then it must be that the weight of the screwdriver is right at the pivot where the prism is. Otherwise, screwdriver would have either rotated clockwise, or it would have rotated anti-clockwise, but none of these things are happening. So it must be that the moment is zero, and then there's only one option left, and that is to say, Well, the center of gravity of the screwdriver is basically here, and that means that the weight of the screwdriver is acting from here like this. And since the weight is a force whose distance is 0 from the pivot right now, it does not produce any moment, and that's why no turning effect is produced. No turning effect, which basically means that the screwdriver will be balanced. Now you might also be asked to identify center of gravity of different objects, so I'll go through all of these shapes one by one. For regular geometric shapes, it's quite easy to identify the center of gravity. For example, for this square, it will be right in the middle, vertically as well as horizontally. This is a symmetrical shape, so it's quite easy to identify the center of gravity here. In this rectangle, again, just measure the distance from the top and the bottom and from either side, and it should be in the middle. For circles again as well, it should be in the middle. For triangle, however, obviously it's going to be symmetrical. It has vertical symmetry, so it's right in the middle, but it doesn't have horizontal symmetry. So if I were to say that this is the height of the triangle, let's say if this was h, then the center of gravity wouldn't actually be right in the center. No, it wouldn't be here. It will actually be somewhere below that point and closer to the base than to the top. You don't have to remember how far up the base it is going to be, but you should have a little intuition while looking at a shape like this that it's not actually right in the middle vertically, it's not closer to the top, but it's actually closer to the base of the triangle. Let's look at the example of this wheel. Now for the wheel, it's actually hollow from the center, but in situations like this, you again have to realize that the center of gravity isn't really a real point, it's an imaginary point. The weight isn't actually concentrated at the center, but to solve problems we can assume that this weight can be concentrated at that point. So it doesn't really have to lie inside the wheel. It could be at a hollow point which is actually not part of the wheel at all, and this is where the center of gravity of this wheel would be, where the red dot is. Similarly, for this empty glass, it would actually be right in the middle of this glass where the hollow part is, where there is air and nothing actually there, but the center of gravity is actually lying in that hollow part. For this baseball bat, you can see that it's not even. This part is much lighter compared to this part, which is much heavier. So for situations like these, you should have again the intuition that the center of gravity will be actually shifted towards the heavier part. So it will not be in the middle, it will actually be closer to the part where most of the mass is distributed. And for all of these objects, that's where you will draw the force of weight from. So to identify the center of gravity is to actually identify the location of the weight force. Alright, now this actually leads us to the topic of stability of objects, and center of gravity can actually help us explain how one object can be made more stable. Now look at this cone which is lying flat on the table. This position 1 is quite stable, and we can, let's say, just say this is the point where the center of the gravity of this cone is. Now the question is, how far can you tilt this cone such that it will actually topple over, such that it will not come back to its original position? Is position 2 enough to make it fall over, or it will come back to the original position? Well, again, what you have to do is look at where the center of gravity is, and also need to identify where the pivot is. So the pivot is the point where the cone is actually in contact with the surface. This will be your pivot in this scenario. In all of these scenarios, this is where the pivot is going to be, where the cone actually is in contact with the surface. Now let's look at the center of gravity. It's still over the base of the cone, and it's to the left of the pivot. So if the weight is acting like this, it means that the moment is going to be anti-clockwise, and if the cone rotates anti-clockwise, it should return back to the original position. So this will return. Let's look at the cone in the third position. What does this do? Well, if you look at the center of gravity, right now it looks like that the weight is right above the pivot. So this is the point where you can say you have reached the limit, and if you go any further, the cone will not actually return to the original position and will fall over clockwise. So this is where, if you might leave it, you will say it's theoretically it's balanced, but you know that if you let it go, it might do any of those things. So you can't go any further than this, and this is what actually happens in the fourth position. You can see that the center of gravity now must be somewhere in this position, and this is how the weight acts. So if you look at the pivot and the position of the weight force, you can see now that the weight force is going to produce a clockwise moment, which means that this cone is actually going to fall over. Now how can we improve the stability of this cone? Well, one of the ways is to use a wider base. Now when you use a wider base, you can see that the cone below stays balanced for much longer. You can tilt it more and more. You can actually give it a bigger tilt than the purple cone above, and still it might actually come back to the starting position. So let's say if this is the center of gravity, and this is the center of gravity here, and this is the center of gravity here, you can see that we have tilted it much farther than the cone which is above, but still this cone might actually come back to the starting position, because with respect to the pivot, the weight is still on the left hand side, it's still above the base, so it will come back to the original position and it will rotate anti-clockwise. So in order to increase stability, you actually can do two things. One thing is to use a wider base. Another thing is to lower the center of gravity. Now how do you lower the center of gravity? What you can do is use a denser material, a material with more density, a heavier material at the bottom than the top. And this is why things that are heavier at the bottom seem to be more balanced and more stable than the objects which are heavier at the top and lighter at the bottom. They will actually topple over very easily. Now there are three different types of equilibrium for objects, and they also have to do with the stability of objects. So you can look at number one here. This is what you actually called stable equilibrium, because if you let the cone sit in this position, the center of gravity is actually above the base and it stays there, and this is why the cone is going to stay stable. It is not going to rotate anywhere, it's not going to go anywhere. Now the second position actually shows you unstable equilibrium. And why is that unstable? Because the base is now so small that this center of gravity can hardly stay above it. When you let the cone go, there is very little chance that the center of gravity will actually stay above the base, because the base is now very small. Initially, in the first picture, the base was very wide, and that is why there is very little chance of the base, the center of gravity staying above the base, and that is why either it will fall to this side or this side, and this is why we call it unstable equilibrium. The third situation is what you actually call neutral equilibrium. And what happens here is, now that the cone is lying is on its slanted surface, so you know it's going to roll around like this. It's going to roll either like this or like this, but the center of gravity will always stay above the base. Now again, the base is very small. This is the base and this is the center of gravity, but no matter in which direction it rotates, the base is always going to be below the center of gravity, and center of gravity is going to stay above it. And that is why its equilibrium will not be, although it can move, but its equilibrium will not be disturbed. We will still consider it to be in equilibrium, or we will still consider it to be a stable object, although it can still roll around. All right.